In Chapter 2, we will learn how to graph all 6 basic trigonometric functions and apply simple algebraic transformations to those graphs. One tool that will be vital in our understanding of those graphs is the unit circle. At this point, we've learned the locations of the common angles in degrees and radians on the unit circle. Today, we're going to expand our understanding of the unit circle. Quick review. Previously in Chapter 1, we evaluated trigonometric functions using a variety of techniques. The first method that we learned was to locate a point, xy, on the terminal side of an angle alpha in standard position, and we found the 6 trigonometric ratios. The second method that we learned was using SOHCAHTOA and special 45-45-90 or 30-60-90 triangles to evaluate the trigonometric functions. A third approach was basic memory. You memorize the values in tables or using the hand tricks. Today, we're going to combine all 3 approaches on the very special and important unit circle, or a circle of radius 1 unit. Let's look at a new perspective of our trigonometric functions. Definition: if alpha is an angle in standard position whose terminal side intersects the unit circle at the point xy, then we're going to redefine our trigonometric functions. So notice we still have an angle alpha in standard position. And previously our goal was to find a point xy on the terminal side of that angle. What's different here is that specifically now the distance between the origin and this terminal point will be 1. So the radius of the circle that we're considering is 1. So how do we find that point xy that is exactly 1 unit away from the origin? Now, we'll talk about how to do that in a minute, but for now, let's see how does the definition of our trigonometric functions simplify. Recall that sine of alpha was equal to the y-coordinate divided by r. Well, in this case, if r is equal to 1, then sine equal to y divided by r reduces simply to y divided by 1 or y. Cosine of alpha previously was defined as x divided by r, but if r equals 1, then cosine of alpha is simply equivalent to x. Tangent of alpha doesn't change. It is still y equals x. So when r equals 1, the point xy is located on the unit circle, and the definitions of our basic trigonometric functions simplifies a bit. Now, to figure out cosecant, secant, and cotangent, we're still going to use their reciprocal relationships with sine, cosine, and tangent. We know that cosecant is the reciprocal of sine. If sine of alpha equals y, then cosecant of alpha equals 1 over y. Because secant is the reciprocal of cosine, if cosine of alpha equals x, then secant of alpha equals 1 over x. And if cotangent is the reciprocal of tangent and tangent equals y over x, then cotangent can be evaluated as x over y. Now, those are defined provided no denominator is 0. If a denominator is 0, we get an undefined trigonometric function. Now that we're working on the unit circle, we can make the observation that the point on the terminal side of the angle alpha in standard position is exactly 1 unit away from the origin, and the ordered pair xy is now given as the ordered pair cosine of alpha, sine of alpha. So cosine of alpha then is equal to the x-coordinate of this point on the terminal side of the angle. And sine of alpha is equal to its y-coordinate. So this ordered pair xy is the intersection of the terminal side of the angle alpha with the unit circle. So now we need to find those specific intersection points between the terminal sides of all of our common angles and the unit circle. To do this, we can scale the special triangles and transpose them onto the unit circle. Let's begin with a 45-45-90 triangle. Recall that the special triangle that we use, the 45-45-90 triangle, we set the legs of that right triangle to be 1, and we calculated the hypotenuse to be the square root of 2. What we want to do is take this special triangle and put it in standard position, but we want to scale it so that that hypotenuse is 1 unit long. Currently, the hypotenuse is square root of 2 units long. So in order to scale it to be 1 unit long, I'm going to divide it by the square root of 2. However, if I divide the hypotenuse by the square root of 2, I'm also going to need to scale the other legs by dividing them by the square root of 2 as well. Notice whenever we rationalize that, we're going to get square root of 2 over 2 for the vertical segment, and we're going to get the same thing, square root of 2 over 2 for our horizontal segment. So when we fit this special 45, 45, 90 triangle on the unit circle so that it has a hypotenuse of 1, then the horizontal coordinate and the vertical coordinate are both square root of 2 over 2, square root of 2 over 2. Remembering that the x-coordinate is the cosine value and the y-coordinate is the sine value, we can use that ordered pair to evaluate sine and cosine of 45 degrees. Let's go through that process again for practice and understanding, but this time let's use our 30, 60, 90 triangle. So our goal now is to scale this 30, 60, 90 triangle so that it fits in standard position on our unit circle. In order for it to fit, we need the hypotenuse to be of length 1. Currently, we have a hypotenuse of length 2. So we can scale it by dividing it by 2. But if I divide the hypotenuse by 2, I need to divide the other legs by 2 as well. Now we can recognize that the horizontal segment of the special 30, 60, 90 triangle with a hypotenuse of 1 on our unit circle, the x-coordinate is square root of 3 over 2 and the y-coordinate is 1/2. Let's go through that process one more time for good understanding. So instead of looking at a 30, 60, 90 triangle, I'm just going to reflect it around and look at a 60, 30, 90 triangle. Our goal is to scale it so that it fits perfectly on the unit circle. In order for it to fit on the unit circle, we need it to have a hypotenuse of 1. You know the drill, right? Right now it has a hypotenuse of 2. I'm going to scale it by dividing it by 2. So that the hypotenuse is 1. If I divide that coordinate, that length by 2, I need to divide the other lengths by 2. Now this special triangle fits perfectly on the unit circle. The horizontal segment gives me the x-coordinate, the vertical segment gives me the y-coordinate. Now let's look closely at this picture. This is an extremely important image, and I want you to memorize this image. This is fundamental for evaluating sine, cosine, and tangent, not just for the angles in Unit 1, but in combination with reference angles, we'll be able to use the information that we see here to find sine, cosine, and tangent for all of our common angles. So let's observe some patterns. Notice for the 30-degree angle, cosine is equal to square root of 3 over 2. So for the 30-degree angle, I'm starting with square root of 3 over 2. And then the sine value is equal to 1/2. Notice when we look at our 60-degree angle, these two switch to give us sine and cosine for 60 degrees. The ordered pair for 45 degrees is pretty simple to remember because both x and y are the same value. And don't forget, we can overlay this with our hand trick where our thumb represents 0 degrees, our pointer is 30 degrees, our middle finger is 45 degrees, ring finger is 60 degrees, and pinky is 90 degrees. For one specific angle, I'll just pick on 45 degrees. To get the cosine of the angle, we're going to count the number of fingers above that finger. In this case, we get 2. We put that number under the radical and divide by 2. To get the sine value, we count the number of fingers below that specific finger, put that number under the radical and divide by 2 and simplify. So reflected in this first quadrant of the unit circle, we have our special triangles, we have the hand trick, and we also have the simplified versions of our trigonometric functions, sine and cosine, representing the x and y coordinates of these points. Now, when we repeat this process for each quadrant, that is, we scale the special triangles and fit them in the appropriate position to determine the coordinates of the intersection point of the terminal sides of the common angles in the unit circle, then we're going to get the complete unit circle. So on the diagram that you see all of our common angles listed both in degrees and radians. In addition, you see the ordered pair for the intersection of the terminal sides and the unit circle. Take some time to memorize this circle. This is fundamental to your survival in trigonometry. It is also fundamental to your understanding of calculus, differential equations, and all of the math classes that follow. So it is a good investment to spend some time learning this unit circle. First of all, memorize quadrant 1. Once you have quadrant 1 memorized, then we're simply going to reflect those points across the x and y axes to generate the ordered pairs on the other side. So let's make some observations. Notice at 30 degrees, or pi over 6 radians, we have the ordered pair square root of 3 over 2 and 1/2. If I reflect that point to the other side of the y-axis, I land at 150 degrees. Notice that on this side of the y-axis, the x-coordinate is negative and the y-coordinate is positive. They have the same absolute values, but the sign of x is negative in quadrant 2. If I reflect that point below the x-axis, down at 210 degrees, notice I have the same absolute values for the x and y coordinate, but in quadrant 3, both x and y are negative. Similarly, if I reflect that point again across the y-axis, here at 330 degrees, I have the same ordered pair, but notice x is positive and y is negative. If we look at the 45-degree angle and observe the ordered pair there, then we're going to notice that every other angle on the unit circle whose reference angle is 45 degrees is going to have the same ordered pair, same absolute values for the ordered pair, but the signs will be adjusted according to the sign, S-I-G-N, of x and y in each quadrant. This is also true for all of the angles with a reference angle of 60 degrees. For example, if I look at 120 degrees over here in quadrant 3, the ordered pair resembles that for its reference angle 60 degrees, but x is negative and y is positive. If we look at the angle in quadrant 3, 240 degrees, that has a reference angle of 60 degrees, we see some familiar numbers with signs adjusted for quadrant. And then finally, reflecting it over here, we see the same ordered pair with signs adjusted for quadrant. The ordered pairs for the quadrantal angles are very intuitive and easy to locate, and they relate to each other as well. Now, once again, if you have quadrant 1 of this unit circle memorized and mastered, and you also understand how to use reference angles, then that is the seed that helps you to memorize the entire circle. Now, just like we had a link for a game to help you learn the angles in degrees and radians, I've also provided a link to help you learn the entire unit circle. So bookmark this link and practice it often. So let me show you how it works. At each angle, you've got 3 blanks. The first blank there is the angle in radians, the second one is in degrees, and the third one is the ordered pair. So the first thing that it's asking us here is to locate 240 degrees. So I'm going to locate that with my mouse in the degree spot. Pi over 2 is the angle in radians, so I'm going to locate that angle in the correct spot. Now, it will also give us ordered pairs, 1, 0, so we locate that outside the circle in parentheses. So you not only get to practice your angles in radians and degrees, but you also get to practice your ordered pairs. So square root of 3 over 2, negative 1/2. I'm thinking of the reference angle 30 degrees there, but x is positive and y is negative. So I would choose the angle with the 30-degree reference angle in quadrant 4. So on and so forth. This is a great way to drill and practice your unit circle. So please spend some time practicing. I cannot stress enough how important it is for you to know this unit circle. You will be sketching this out on papers from now until differential equations, so invest some time and learn it well. Flipping over to the next page of our notes, we'll consider example 1, and we'll talk about how do we use the unit circle to evaluate our trig function. The instructions state, use the unit circle to find the exact value of each trigonometric function. So we need to find sine of 60 degrees. So if we scroll back to our unit circle and we look at 60 degrees, we need to find sine of 60 degrees. According to our new definition, sine of 60 degrees is equal to the y-coordinate. So we can see here that sine of 60 degrees is equal to square root of 3 over 2. Example B, we want to find cosine of 5 pi over 4. So if we locate 5 pi over 4 on our unit circle, cosine indicates we're looking for the x-coordinate. The x-coordinate there is negative square root of 2 over 2. So cosine of 5 pi over 4 is negative square root of 2 over 2. Tangent of negative 120. Now remember, positive 120 is this distance, so 30 degrees past the 90 degree mark. But I want to go negative 120. So I'm going to rotate that same distance in the negative direction. Now we need to calculate tangent of negative 120. Tangent is the y-coordinate divided by the x-coordinate. So we're going to evaluate the y-coordinate negative square root of 3 over 2 divided by x-coordinate 1/2. When we cure this complex fraction by multiplying the top and the bottom by the denominator, we end up with a value of negative square root of 3. Let's look at cosecant of 11 pi over 6. So on our unit circle, we'll first locate the angle 11 pi over 6. Recall that's the angle in quadrant 3 with a reference angle of 30 degrees. We need cosecant of 11 pi over 6. Recall that cosecant is the reciprocal of sine. Sine is the y-coordinate. So here we're going to evaluate 1 over the y-coordinate, or 1 divided by negative 1/2. We can multiply the top and the bottom once again by 2, and we end up with negative 2 for the value of cosecant. Secant of 270, remember secant is related to cosine, so if I can find cosine of 270, I can get secant of 270. So if we rotate to 270, observe cosine, the x-coordinate there is 0. Secant is the reciprocal of cosine. In this case, it would give us 1 over 0. That's no good. We're going to get an undefined value. Finally, let's evaluate cotangent of 5 pi over 3 using our unit circle. First, we're going to locate 5 pi over 3 on our unit circle. Recall that is the angle in quadrant 4 with a reference angle of 60 degrees, and we want to find cotangent. Cotangent is equal to the x-coordinate divided by the y-coordinate. So we will evaluate 1/2 for the x-coordinate divided by negative square root of 3 over 2. Now here's a shortcut. If your denominators match, they will cancel. So we're going to have 1 divided by negative square root of 3. Now once again, let me get some space down here. It's customary to rationalize the denominator in trigonometry, so we will do that, and we get the exact value for cotangent to be negative square root of 3 over 3. So that is how we can use the unit circle to efficiently evaluate our trig functions. It's incredibly efficient when you don't have to look at it, but you have it memorized.